Hello all, I welcome you all to the 10th lecture in this course E690 ATM. We'll have a short recap now and then we will continue with our results from nearly free electron model. And at the end of this lecture, we will talk about the tight binding model and what we can infer from them. For the past few lectures, we spoke about crystals and structures. We spoke about symmetry and most commonly seen lattice systems, cubes, body-centered, face-centered cubes, external closed pack, and such. We saw about the periodicity and the reciprocal lattice. We saw how the reciprocal lattice volume should be inverse of the real lattice volume, and the reciprocal lattice vectors are inverse of the real lattice vectors. And one condition which will enforce all these things is this particular one: e power ig, g being any reciprocal lattice vector and r being the periodicity of the real space lattice. This should be 1 uh, for the conditions to satisfy, for a vector to satisfy being a reciprocal lattice vector. It should satisfy this particular condition. And we saw that in any k in Fourier space, if it can be represented by reciprocal lattice vector, then they should contribute to the solutions in real space lattice. So the real space lattice has some periodicity. It has some contributions in its Fourier series. What case can contribute to the Fourier series? Those cases are actually reciprocal lattice vectors or some linear combination of reciprocal lattice vectors. Right? We saw about electrons in periodic potential, and we spoke about the Bloch's theorem, the solution to the Bloch theorem. One particular thing which has to be remembered is there are two ways to write the Bloch theorem. One is you take the free electron solution at any point r, then its translation to by any reciprocal lattice vector is equivalent to multiplication by this phase factor e power I k dot r is multiplied if you translate a solution at any point r by a reciprocal lattice vector. There are two ways to write this. You can write it in this particular fashion, like your any solution psi of r can be written as uk, where uk is some function which has the periodicity of the lattice multiplied by the plane wave. The second way to write this is any translation by reciprocal lattice vector is equivalent to multiplication by a phase factor. Both of these guys gives the same meaning. We spoke about filling the electrons from k equal to 0 till some point. As k values come close to the Brillouin zone edge or first reciprocal lattice vector, its values, its wavelength is close to the interatomic space. We spoke about Born-Karman boundary condition, and we proved that your k values are discrete because of the boundary condition. A simplest way to remember this is, in a crystal, why does this periodicity come? If you think about this, in the crystal, the smallest k value means the largest wavelength, right? So the largest wavelength should at least start at the beginning of the crystal and end at the end of the crystal, right? If it does not end, that means that there will be some reflection of this particular wave. It is to satisfy this to tell you that you have a finite crystal in the real space. For instance, what we mean is, if this blue ones is the real space size of the real space crystal, the wave with the smallest k value or the largest wavelength should begin at the start of the crystal and end there, or should have the same value at both the edges, right? This is what finally gives you the smallest k value that you can have, right? So once you know about the smallest k value, you have a one-dimensional system. We saw that its energies bunch at the lowest energy levels. A 2D system will have constant density of states, and a 3D system will have a parabolic density. With all these things, we spoke about a Fermi sphere or the Fermi surface. Is in a 3D material, you start occupying k values which are similar in all directions, kx, ky, and kz. The last k value which is being occupied is called as the Fermi wave vector kf, and the energy corresponding it is called as the Fermi energy. In three-dimensional space, it turns out to be a sphere, so it is also called as Fermi sphere or Fermi surface. The surface which holds the last electron at 0 Kelvin is called as the Fermi surface. right? So with that, we also finally showed with the nearly free electron model, you can also show that you will have the existence of a band gap that is shown that if you have k values close to the Brillouin zone edge, or if you scatter the k values by, if the k, I mean, if the electrons get scattered by a reciprocal lattice vector, then they start to form what is called as standing waves, right? So this is what we saw previously, and we showed that as you start increasing k values, when the k value becomes close to pi by a, half the reciprocal lattice vector, then the electron at this particular point is getting scattered back to the k prime point, right? And hence the separation now is about the reciprocal lattice vector b. And these two electrons now will interfere, giving you a standing wave instead of the plane waves that we saw previously. Right? So this is also called as the Bragg reflection at zone boundaries. It's called a zone boundary because this is where the Brillouin zone ends. You typically draw the Brillouin zone as perpendicular bisectors to the reciprocal lattice vectors, right? So with this, we also showed that you can also prove the existence of band gap by two ways. The second one is the Croney-Penning model. We won't go into details, but then we showed if you assume as a periodic lattice potential, there will be certain k values for which there will not be any solution. That's because the right hand side of this equation can turn to have values greater than 1, and hence there will not be any valid k where this equation will be true, right? So with this, we will talk about we'll go to what we will want to see in today's lecture. That would be about Fermi surfaces and tight binding. So we stopped at this particular point where when the k values reach the zone boundary is plus or minus pi by a, it starts to interfere and scatter back, right? So in 2 dimension, if you draw a circle, as the k value here reaches g by 2, you see a discontinuity at these points, right? But then the Brillouin, so this is what is called as a Bragg plane, because these Bragg planes are regions where you have this X-ray kind of diffraction. But you see that you have a lot more of these Bragg planes in any two-dimensional crystal. Even here, you have taken a two-dimensional crystal. Let's assume the reciprocal lattice points are like this. So you have the first point, the second point here, the third point here, 4. You have the fifth somewhere again here, right? Sixth here. Sorry, this should be here. So if you draw perpendicular bisectors to the nearest neighbors of this one, you will see the first one here, second one here, third here, and fourth here, right? And the region bounded by this is called as the first Brillouin zone or the first Wigner-Seitz lattice, correct? So here you can clearly see there are 2 points P and P prime which are of equal energy. They are separated by one reciprocal lattice vector, right? So this is B by A in G by 2 in one direction. This is G by 2 in another direction. The summation of these two will be G, correct? So this P and P prime are points which are separated. So they basically by reciprocal lattice vector. So they should start to interfere, right? Similarly, if we go along this line here, you will see that you will have discontinuity in the surface like we saw here at points K, X1, X2, and X3, right? You'll see that it interferes with the Bragg plane in all these points. You have the first Bragg plane here. You also have the second Bragg plane here. But this plane is introduced because this is the Bragg plane of the second nearest neighbor, right? So this line, as we draw here, becomes the perpendicular bisector for an atom here, right? Similarly, this one is a perpendicular bisector for an atom here. Similarly, this one is a perpendicular bisector for an atom here. And obviously, these are not the nearest neighbors, but the first nearest neighbors of this atom that we are considering here. So you have many more of these points and you'll start to have discontinuities in energies in these points. So how do we start visualizing this? To do that, we have to go through by drawing constant energy surfaces. So let's start at this point as we saw previously and start drawing circles having constant energies. These are separated by the same k value from the center, right? So they will have constant energies. You draw this circle once. This will be the first energy. This will be second energy. Now the third circle will start to meet with this Bragg plane, right? And whenever it meets the Bragg plane, there is a small deviance from the circular behavior and there is a discontinuity, right? Similarly, you will see the fourth plane here, fourth circle, all of them having discontinuities at these points. But when you come to look at these circles, right, you have to also notice that you see that it was also a part of a circle from this particular point, right? Because of these interferences with these Bragg planes, you will start to see these circles cropping up. These are all part of circles initially from this particular point, right? And these areas, that is Q dash CB, so this triangle, this trapezoid and this trapezoid are not from the first Brillouin zone but from the second Brillouin zone, right? Because this perpendicular bisector came about by having a perpendicular bisector to this lattice vector, which is not the first lattice vector, first Brillouin zone lattice vector, right? Now we take this, and in the reduced Brillouin zone behavior that we saw previously, we saw that any point outside the first Brillouin zone can be represented by a point inside. You start to fold it back, right? So you fold these triangles back. You fold this trapezoid back into the first zone. How will it look? It will look like this, correct? So basically, this trapezoid is folded back from here, and this triangle was folded back from this particular point. And similarly, this one was folded from the top, right? And here you can clearly see you have Q dash and Q double dash coinciding at this point. If you compare at this particular here, Q dash and Q double dash are equidistant from the center. They are all separated. When they are equidistant, they have similar energies, right? And they are separated from the same reciprocal lattice vector, right? They are separated by reciprocal lattice vectors. So they are all equivalent in energy and they interfere with each other. So you form one particular point in the reduced Brillouin zone, which marks this set Q dash and Q prime. The same thing can happen in A dash, B dash, and C dash, which can again be seen here. A dash, B dash. All these things are equidistant from the center point here, right? So they all form these circles. So if we now draw the first zone and second zone independently, the first zone has these circles and some small deviations of the circles as we saw previously, right? So this one is the first one. The second one has these cusps. These are cusps, right? These cusps arising because of fold back. You fold back from the first zone and then you get these particular points. Right? So this is how Fermi surfaces are drawn. A different way to imagine this is you take this particular point and you draw this first Brillouin zone and the first and a Fermi sphere, right? So the blue line is a Fermi sphere. You can do this for n number of lattice points. So you have the first lattice point, second lattice point, and third lattice point, right? So basically you draw circles of constant radius around each of these lattice points, and its intersection in one reciprocal lattice. So this is an intersection of the second of a sphere from the second lattice point in the first zone. This is same as folding back of the second zone in the first lattice point, right? So whatever that So if you see, this is symmetric around this point. This area is the extension from the first zone, and these lines were a part of the circle drawn from the second lattice point, right? So this is called as the Harrison's representation. You can either draw the first zone and start folding it back, or draw independent circles from each of these lattice points. So when we do this, the first zone is a pure sphere, as we drew here, and the first zone is this rectangle here, right? Now the second zone is folded back, and you will start seeing regions like this, right? And constant energy surfaces around this particular point. So the Fermi sphere here is particularly important because it tells you about the current characteristics and the resistivity of this particular material at any temperature. You see that the constant energy surfaces at this particular point seems to have this kind of a hill, right? This comes about, so basically it climbs up and then it reaches to a point. Here it ends with a surface, and the surface is basically the Brillouin zone edge, right? It comes about once again because of this behavior. You see here, what was supposed to be a straight line now curves back, right? The same thing will happen in several directions, and it is this curving is what is finally seen here. You see something to curve like this to give you a kind of a hill with a small density of states which have constant energy, right? The constant energy circles now increase in dimension as you go down, but your Fermi level is here, which has the small circumference, and this small circumference gives you the density of k states in which you can have a change if you have a potential, right? So basically, instead of a sphere, right, so which has constant k values, states with constant energy throughout, you have, let's say, a hill where the density of states which have constant energies is significantly smaller, right? So these things will continuously modulate the way conductivity changes in a material. And once you start populating these materials at various temperatures, you start seeing where the Fermi surface is, what is the electron concentration above the Fermi surface, and it tells you about the conductivity of this metal, right? So with this treatment of Fermi sphere and Fermi surface, we will stop our treatment on nearly free electron model. We'll come back to this treatment later on when we talk about conductivity using the Sommerfeld description and such. We will talk about Fermi sphere again. But this is a conclusion or some point at which the nearly free electron model stops, right? It gives you some feel about electron concentrations in crystals with periodic atomic potentials. Right. So till now we have spoken about electrons as free waves, right? Something around these lines, and we have not talked about electron wave functions which are bound near the atom core, which we know will exist, right? So I have a positive atom core. We know that there exists 1s, 2s, 2p, and so on, and so many atomic orbitals. But we forgot about them, right? We spoke about only electrons which are almost free, electrons which are in the conduction band, electrons which behave like plane waves, right? So while this model is relatively true when the atomic densities, when the atomic distances are small, the potentials are very small, and the most of the electrons which are conducting, which contribute most of the electrical properties, happens to be in the conduction band. But in situations where the atomic distances are large and the conductivities are small, then you will have contributions from the atomic orbitals, and that is what we will see. We will see another equivalent method which can also show an existence of band gap, which is called as tight binding. But before we go there, let's talk about the atom first, because we have to show that there exists 1s, 2s, and 2p. What does what are these indices mean? there exists some discrete energy states in an atom. We will go through this derivation very quickly. We will not go through the math, but we will just show to you that there will be discrete states in an atom. They are named S, P, D, and F because of some criteria. And once these are there, we will talk about the formulation of tight binding. To solve the problem of an atom, you once again solve the Schrödinger's equation. But the difference now is that your del square is now in a spherically symmetric potential. When you have a spherically symmetric potential, you stop using the Cartesian coordinates and then you go to the spherical coordinates with r, theta, and psi. So you split the nabla square. This is a Laplacian to this particular form. This is something that you must have seen. And we once again use the wave function separation of variables. You remember we did separation of variables in spatial and time. We will separate the radial, angular, and azimuthal angles, and we separate it in this form. We know the potential is Coulombic in an atom, right, which goes down as 1 by r. This is the potential of charges. So the electrical charge has 1 by r potential. It's called as the Coulombic potential. It reduces as 1 by r as we go radially. From this to this point, the potential drops, right? So if I substitute this into our Schrödinger's equation and we separate the variable, the radial component will look like this: minus h bar square by 2m d square u, capital U is a radial component, and its potential has two terms. One is the attractive Coulombic force, and the second one is a centrifugal ejection force which acts along the radius, right? It's like an atom is moving around in circles. There is, when it is moving around us, there is a force which acts outwards of the center along the radius, and there is a force or potential which pulls the electron inside, right? And it is the balance between these two forces that makes the electron to be stable. Here we have L into n plus 1, which is a separation constant. Whenever we separate variables, you'll have three equations which all of them equal to some constant, right? Which is L into. We make it to be like this. We will see where this is used later on. So I write the Schrödinger's equation once again. The solution for this U can be written in this particular format. It's just a mathematical treatment, right? So instead of r, we do a change of variable. We write r as, rho as twice r by NA. N is any constant, and A naught is called as the Bohr radius, which comes out to be constants based on the atomic environment, right? So this is magnetic permittivity, this dielectric permittivity, and such. Right. So U has this particular behavior, some constant times e power minus rho by 2 into rho power n. We substitute this into this equation, we can see that it satisfies the eigen equation. The total solution looks in this form. You have a constant multiplied by the radial component, you have the Lagrangian polynomial, and you have the spherical functions, right? So these are called the spherical functions. You have three unique integers which are used to define the wave function. One is total capital N, which tells the total number of nodes in this wave function. For instance, we have 200 as seen here, or 200 as seen here. This tells you how many total number of nodes it has. There are m angular nodes which forms ring in the xy plane. For instance, if this is the xy plane, let's say, right, so this is z, this is xy plane, how many angular nodes it has, right? And L minus m is the angular node that occurs in the vertical axis. For instance, this is, let's say this is the vertical axis, you have a node here, and this is L minus m. So this is L and this is m. 1 minus 0 will be 1. So you should have one angular node in the vertical axis, right? Similarly, you have, let's say, 2 minus 1 here. You have one node in the vertical axis. So let's say, take the example of 2. You have two nodes in the vertical axis, right? So you have one node here, another node from these two, right? These two will form another node, and you have another node because of these two. Node is a point which remains stationary in space, right? Basically, it tells you the frequency of oscillation, determines the frequency of oscillation. Higher the number of nodes, higher will be the energy. So as you go down here, you increase the energy of the wave function. You also increase the nodes. Here, if L equal to 0, we call them spherical orbitals. So which means that you do not have any angular nodes in the vertical axis. L equal to 1, we call the subsequent m minus 1, 0, 1 to be as pre-orbitals, right? So basically 2, 1, 0, 2, 1, 1. So basically these are the spherical. So this is called px, py, right? So you can see them kind of oscillating around the, this is the y-axis, this is around the, let's say, z-axis, right? And if L equal to 2, you get subsequent minus 2, 1, 0, 1, 2 as d orbitals. What we want to take away from here is if you solve the Schrödinger's equation under a Coulombic potential, in spherically symmetric Coulombic potential, you will get wave functions which can be uniquely determined by 3 integers, which is n, m, and l. So basically, you have energy with increasing energy levels. So you will have 1s, 2s, 2p, 3s, 3p, and such. And this goes on. And we know how the energy levels align up, right, as we go higher and higher. Now that we understand that an atom typically has wave functions in this particular way, we look at solutions using tight binding approximation. We will go slowly to understand why this is called a tight binding approximation. But at the outset, what it means is, let's say you have an atom here, and its potential is Coulombic, as we say here, right? And if you bring another atom close by, each of these atoms have energy levels. Let's say call this 1s, 2s, 2p. Right? So basically, let's say 1s is like this, 2s is like this, and let's say 2p is something of this. Right? Each of these two atoms have this. So now the question is, if I bring them together, move them together, reduce the atomic distance L, what happens to these wave functions? How do they interact with each other? So these are the questions that we want to talk about. As we saw previously in the perturbation theory, we will try to solve this using the perturbation method. We will talk about the Hamiltonian in an atom as HAT, and any wave function here is written as psi A. So obviously the Schrödinger's equation in an isolated atom can be written as HA psi A is EA psi A. This is the standard Schrödinger's equation for an isolated atom, right? And when we bring this isolated atom in a field close to another atom, we will assume that the Hamiltonian is not largely changed, but then there are small perturbations, right? So what we do is we write the perturbed Hamiltonian H is written as the atomic Hamiltonian HA plus del U. Del U is the perturbation, and we write psi k as the wave functions of atom in periodic potential. While psi a's are wave functions in an isolated atom, psi k's are wave functions of an atom in periodic potential, right? So our final problem is to solve this Schrödinger's equation. Hk psi k is E psi k. And the problem is, if H can be written in this particular form, how does this E change from the atomic energies E? This is what we are trying to solve now. To do this, we are going to assume solution. So we already know that we are talking about periodic atoms. So when we talk about periodic atoms, obviously the solution has to be a Bloch wave. As we saw previously, psi k are solutions. So if the solution is translated by a lattice constant r is equal to the multiplication by a phase factor e power I k dot r into psi k of r. This is the standard Bloch equation, right? So you know this. Now, what we are going to do is we are going to take solutions which look like this. What it means is by psi a were atomic orbitals, atomic wave functions as we saw previously, right? So I am going to take that the electron wave function in a periodic lattice is a summation of the wave functions which are just lattice translated. L is some lattice translation, right? So what I mean is, let's say I have an atom here, I have another atom, another atom, another atom, each of them separated by L, right? And if this has a wave function like this has one psi a here, this is psi a, this is psi a, this is psi a, right? These are atomic orbitals. When I mix them together, I find the final psi k to be a summation of all these things, right? But then you know that this psi at this lattice point, let's say the first lattice point, if you translate this by a reciprocal lattice vector L, then it has to be phase multiplied, correct? So it is just a this is written in a different form of the Bloch equation. So all I'm writing is at this point, I can write as the wave vector here is a summation of the wave function at all the lattice points multiplied by its corresponding phase factor. That's it, right? So basically it's summation of the wave function at all lattice points multiplied by the corresponding phase factor e power I k L into psi a of r minus L. Now you can easily prove that this will this will satisfy the Bloch equation. I'm not going to go through this. You can do it as your homework. So basically, if I assume the wave function at any point to be a summation of wave functions at the entire lattice, right, then that particular wave function will satisfy the Bloch equation. But the question here is, what wave function will I add? So this psi k is an atom, is an energy of an, or is a wave function of an electron periodic in a periodic lattice, right? And I'm saying it is summation of atomic orbitals. The question can be, what atomic orbital will I take? So the simplest one will be to take a summation of atomic orbitals, right? So this is the crux of the tight binding approximation, or it is called as a linear combination of atomic orbitals. So what I do is I take a linear combination of atomic orbitals at each lattice point. Let's take this as one lattice point. It has several atomic orbitals. Let's take this to be 1s, 2s will be like this, 2p, let's say like this. I take this psi of r as a linear combination of atomic orbitals. What atomic orbitals that I don't take, I can take the bn's to be 0. Which ones will I take? I will have bn's to be a significant number, right? So if I take this psi r to be like this, and I write the Bloch equation to be a summation at all lattice points, some linear combination of atomic orbitals. So I take some linear combination of atomic orbitals and sum it from all lattice points. That will be the solution of my wave vector. This is the simplest way in which it can be written, though not the cleverest way, but this is how it is written in the linear combination of atomic orbitals. As we saw previously, the Hamiltonian appears to be in this particular format. We can go through the math, but I will just tell you the important points. Okay, so now I just substitute this h to be here, and then I act from the left hand side psi m. This is something that you must have seen previously as well, right? If I act through this, I can reduce. There are two things which have to be taken into consideration here. I think this we will remember from our treatment in of quantum mechanics. This bracket basically means as an overlap integral. So here psi m is an atomic orbital. I'll just write here. So basically it is psi m acting on psi r. This is psi k of r. Okay. Psi k of r, as we saw previously, is a solution of an electron in the entire periodic lattice. Right. So basically, let's say this is the periodic lattice, and psi k has some form, which is also periodic. This is psi k, which extends throughout your crystal. And psi m is something which is localized in this particular atom. Let's say is like this. What is the overlap of these two is this particular value. Is psi m overlapped with psi r. Right? If it so happens that psi k instead of this function that we wrote here, let's say if it is flat 0 and has something only here, the overlap will turn out to be 0. Right? The overlap means I just multiply one with the other, and you will have a non-zero value only if both of them exist. You will have a 0 or a small value if one of them does not exist. Right? So this is the meaning of this overlap integral, or the bracket notation as we write here. If you go through this derivation, which is not very hard, we can go through this if you are interested in our interaction session. But for the purpose of this lecture, all you have to take away from here is the overlap of psi m, any atomic orbital psi m, with the lattice function psi of r. This is k, and this I've removed k here because it is not relevant, right? So the psi k of r you can write as these two summations. The first summation is summation of over all atomic orbitals that you take at one lattice point. The second summation is a summation over all lattice points. Right? You have two summations, right? It is the overlap of this psi m, one atomic function, versus the whole lattice, whole wave function, which extends through the whole lattice. This summation can be split into two components. One component when r equal to 0. When r equal to 0, it is the same lattice point itself, right? At the same lattice point, then this bn, so basically this psi m will be orthonormal to all the other atomic orbitals unless it is degenerate, right? So psi m star psi n is delta mn in an atom. So at r equal to 0, psi m star psi an will give you only bm, the component along this particular value, right? All others will turn out to be 0. For r not equal to 0, then you have this huge summation. So we can do this for the other term here. So basically you have two terms here. One is this overlap psi m psi r, and another one is psi m overlapping with ur. Ur is the periodic perturbation that we saw previously. Ur acting on psi r. So what is the solution for ur acting on psi r and its overlap with psi m? You will get once again this big equation. This one when r equal to 0, and this one when r not equal to 0. Whatever be our previous discussion, right? The crux of all these things lies in this equation. Though it seems big, the most important characteristic comes here, right? So all of these things are overlap integrals, right? As I said before, this is at r equal to 0, and this is at r not equal to 0. So basically, if I'm talking about this atom, this term comes at this place, and this term talks about wave functions in other lattices, which is phase multiplied to bring here. This is the Bloch expressions, right? So now let's go through each of these terms one by one. Let's talk about only this, right? So here I have psi m, which is the atomic orbital here, whose overlap I'm talking about atomic orbitals in a different place. So what is the overlap of an atomic orbital? Let's say this atomic orbital overlap with this will be a very small number, right? Because this one, as it goes here, it's almost 0. Similarly, this one as it goes here will be almost 0. Only things which will survive is when R is a very small number. Only probably the nearest atoms can probably contribute, otherwise this term will be 0. Similarly, here, let's say in this particular point, when we are very close to the atom, the perturbation U of R is 0, right? Because the periodic potentials change the potential only far away from the atom. Close to the atom, this U of R is 0, so even this will be a small number. Even here you have U of R, so basically these two will be small numbers close to the atom. So in effect, the entire right hand side is going to be a small value. So what it means is Em is energy of the atomic orbital and Ek is the energy of the wave function, right? If Bm is non-zero, that means that you're talking about an orbital which contributes to the electron wave function overall in the crystal, right? That's why Bms are values of the or coefficients of the atomic orbitals which contribute to the electron wave functions in the crystal. If this is non-zero, Ek minus Em must be small. What it means is the energy values are very close to the atomic energy values. If Bm is 0, in the sense that it does not contribute, then it does not really matter, right? So for Bms which are non-zero, which contribute to these wave functions which extend to the entire lattice, these Ek should be similar to Em. Right? And the linear sum of atomic orbitals can only have terms whose energies are close. So these Bms can have non-zero values only when Ek equal to Em, right? Because the right hand side is small. If Bm should be non-zero, Ek should be very similar to Em. That is, this Ek minus Em must be a small number. We can calculate this for a very simple 1s orbital. So what happens is, if you go through this derivation, you will see that the energy of the electron throughout this crystal is very close to the energy of the 1s orbital minus the overlap functions. And if these values are small, so obviously Ek will turn out to be Es. So this is what is the conclusions from the tight binding approximation. If we come to this particular point, so here let's say that we have an atom whose energy levels are n equal to 1, n equal to 2, and n equal to 3. And if we have a linear chain of n atoms, so obviously we will have n degenerate energy levels, right? So here we are plotting the energy band separation as the atomic spacing is reduced as we go from left to right, right? If the atomic spacing is really large, then all the overlap functions will be 0, right? Because the atomic spacings are very large, two wave functions will never meet, particularly for the points where the energies, where you have, for the electron functions which are very close to the atom, that is 1s and 2s, you will not have a lot of overlap. So the energy levels will not split. Your Ek's will be very close to Em. So let's say this is Em. This split is Ek. Ek is very close to Em. As you reduce the atomic spacing and come to a point where you have significant overlap, so again, if you come to this equation, now the right hand side, if you start to have significant overlap, then the right hand side starts to have significant value, will not be a very small value. If the right hand side turns out to be not a small value, you can see that the Ek's can now significantly vary from Em, even for Bm not equal to 0, right? So if we start having the overlap values, then you will have energy levels not equal to 0 even away from the Em energy level. So this is the Em energy level. You will have a spread. As you start decreasing the atomic spacing, more and more you will start having the atomic overlaps, and these energy levels will expand. This is what you will see for n equal to 2 and n equal to 3 as well. But remember, your n equal to 3 and higher numbers, right, n equal to 4, will have lot more degeneracy, right? So basically, let's say 2s has 2p energy levels which are degenerate, 2px, 2py, and 2pz are degenerate, right? Similarly, 3p will have a lot more degenerate energy levels. When you have degenerate energy levels, you will have non-zero values even here. Sorry. So basically, even in the same atom, even when R equal to 0, you will have non-zero values. So you will start to have spreading even when the atoms are slightly away, right? So as you go higher and higher in the energy levels, you will start seeing spreading in the energy levels even when the atomic spacing is really large. Now, depending upon the atomic spacing, now you can see that energy levels which were largely separated now started to have bands. And because now that you have bands, you'll start to see energy gaps between the bands. If let's say this is the atomic spacing of silicon, you will see the first band here, the second band here, the third band here, and so on and so forth as you go forward. Even here you have a band. One has to remember that you have band even when the atomic spacing is here. But just that they are all degenerate. All the n atoms have the energy levels at the same point. So all the energy levels have the same energy. But here, when the bands start to overlap, the energy levels start to separate away because of the overlap functions, and you start having bands. There are two ways to look at it. You can come at it from the Pauli's exclusion principle as well, which tells you that if the atomic orbital starts to overlap, they'll have to repel each other away, right? So the perturbation theory also tells you that if you have two atomic orbitals which have closer energy, the interaction will push one down and push one up the other side, right? That also will cause this band separation. The overlap integral from the tight binding approximation from this equation also shows you that you should have separation in the band energy levels. And the simple Pauli's exclusion principle also tells you that you have to have energy levels which move away because they cannot have the same, all the four quantum numbers the same. And depending upon where is the optimum separation between the atoms that comes about by the Reynolds-Jones potential, if you will solve, that tells you the existence of bands and the existence of gap between these bands when atoms come together to form the solid. Right? So with this treatment of tight binding, we will stop here, and the next time we meet, let's talk about other means to generate the band structure and the thermodynamics and statistics of electrons. Thank you.